Welcome to the Explainer, everyone. If you're tuning in, it means you are ready to seriously level up your understanding of how machines actually operate. Today, we're unpacking the core mechanics of Grade 7 robotics. We're going to focus specifically on that really thrilling transition from basic, kind of rigid movements all the way to smart, autonomous programming. We'll be drawing directly from the curriculum for Units 1, 2, and 3 to figure out exactly how things like sequence, loops, and decisions make robot behavior truly flexible. But first, I want you to think about something for a second. Why do robots crash? You know the drill. You build a robot, program it to move, and everything seems perfectly fine on your testing table. But the exact moment you put it on the floor, bam! It runs straight into a chair, drives right off a step, or stubbornly drills itself into a corner while the motors just whine. So why does that happen? Well, it's because the real world changes, and rigid basic programming simply cannot adapt to those changes. Okay, let's dive into this. Here's our map for today so you know exactly how we're going to build up your knowledge. 1. From rigid to flexible. 2. Loops and decisions. 3. Sensing the environment. 4. Tracing a control flow plan. 5. A robot misconception check. And finally, number 6, the exit question. Section 1. From rigid to flexible. So to really upgrade our robot, we first have to understand its most basic operating mode from Unit 1. In basic robotics, everything relies entirely on a sequence. A sequence is simply a set of precise instructions executed in a very specific order. Think of it like following a super strict recipe to bake a cake where absolutely zero adjustments can be made. You turn the motors on, you move forward for 3 seconds, and you stop. Simple, right? But here's the problem. A sequence cannot make adjustments. If a wall is suddenly placed in front of the robot at second 2, well, the robot doesn't care. It's going to keep running its motors for that 3rd second, pushing blindly into the wall, simply because it's rigidly following its sequence. Moving on to Section 2, Loops and Decisions. Because the real world is entirely unpredictable, a simple sequence just isn't going to cut it. And that brings us to Unit 3 of the curriculum, and really the ultimate upgrade to our robot's brain, program flow. To upgrade from that rigid sequence, our first tool in program flow is the loop. Loops are commands that repeat an action or a sequence of instructions multiple times. Instead of a programmer having to manually type out, move forward, check path, move forward, check path 100 times over, they can just write that instruction once and tell the code to loop it. It saves a massive amount of time, keeps your code highly organized, and allows the robot to run continuous operations. So the crucial point is understanding decisions, which are also known as conditionals. These are programming structures that choose an action based on a specific condition being met. Honestly, this is where the magic happens. Instead of blindly executing a command, the robot actually checks a condition first. Like, is the path clear? If yes, move forward. If no, stop. Decisions are what actually make a robot's behavior flexible and adaptable to an ever-changing environment. Now, what's really interesting here is how clearly we can contrast these two behaviors directly. Think about the basic sequence from Unit 1. Move forward 5 steps. It's completely rigid. Now compare that to the Unit 3 program flow. Move forward until you see a wall. That word until is the conditional decision. It's a total game changer. This dynamic allows the robot to react to its environment rather than just blindly moving, ensuring it doesn't crash, whether that wall is 2 steps away or 20 steps away. Section 3. Sensing the environment. But wait, how does the robot actually know when it's reached a wall? This is exactly where Unit 2 comes into play. The answer? Sensors. Sensors are the physical hardware that gathers input data about the environment to trigger those conditional behaviors we just talked about. If conditionals are the robot's logic, well, sensors are its eyes and ears. Without sensor data, things like distance measurements, light detection, or touch, the conditional program literally has no information to base its decisions on. Section 4. Tracing a control flow plan. Let's move to and see how this builds. Now that we've got our core components, sequences, loops, conditionals, and sensors, it's time to put them all together. We're going to trace a control flow plan, which is an absolutely vital skill for predicting robot behavior. Let's trace the logic step by step. Step 1, we start the loop, telling the robot to run this routine continuously. Step 2, the robot checks the sensor data to gather current environmental input. Step 3, the program runs a decision, asking the conditional question, is the path clear? And finally, Step 4, based on the answer to that decision, the robot executes an action, either moving forward or turning. Then, because of the loop, it immediately jumps right back to Step 1. And this brilliantly illustrates the direct relationship between what the robot senses and what it does. On one hand, we have the specific input data from the environment. On the other, we have the conditional response triggered by the program flow. If the sensor detects a wall, the condition is met to trigger a 90-degree turn. If the sensor detects a clear path, the condition dictates moving forward. The software logic perfectly and entirely relies on that hardware input. Section 5. Robot Misconception Check. Before we wrap up, we need to pause for a second to ensure we truly understand the underlying mechanics here and avoid a really common learning trap. I want to ask you directly, does the robot truly know a wall is there? Like, when it stops inches from an obstacle, is it because it has a brain and understands danger or is alive? The answer is no, and this reality check perfectly grounds us. Robots only read input data and execute pre-programmed conditional behaviors based on that specific data. A robot isn't alive. It doesn't actually know what a wall is. It simply receives a numerical value from a distance sensor, feeds that number into the control flow plan that you gave it, and activates a motor sequence if the condition is met. You are the brains of the operation. The robot is just executing the flow. Section 6.
The exit question.
And that brings us to our final test. A key outcome for Unit 3 is the ability to debug and predict program behavior based on everything we've just covered. So here is your exit question. If a robot is programmed to loop a forward sequence until its sensor detects a wall, what happens if that sensor completely breaks while the robot is moving? Think about how the conditional logic relies on the input data and what happens to a loop if its exit condition can literally never be met. I'm going to let you ponder that for a moment. Trace the logic, figure it out, and use it to debug your very next build. Thanks for joining me on this explainer, and keep building smarter flow.